Okay, so we discussed user interface last time, so we'll briefly review the general usability principles. You should have consistency, that is similar actions in similar situations, so that the user doesn't have to know many different ways of doing the same thing. There should be identical terminology in prompts, menus, and help, and accuracy and completeness, that is, the information to which the user has access must be accurate. The user often is inundated with information, but it's the wrong type of information. So you should try to give the information, the necessary information to the user, but not more. The task should not take longer to do than with the system than without the system. So that's why the reason you're developing the system is to increase the user productivity, right? So shortcuts can help, like the popular shortcut Control-C, Control-V on Windows. There should be informative feedback for user action, but do not overdo feedback. For minor actions, you don't have to provide feedback, but for critical actions, for example, in Windows, if you're deleting a file, you should try to warn the user. But if you're just moving a file or copying a file, you don't have to provide any feedback. So closure, that is, user knows that a task has been completed. So if a user registers for a course, at the end you pop up a dialog to tell the user that you have successfully registered for Comp211 for 2008. So the user knows that it's done. So he has closure. Error handling minimizes a user's opportunity to make mistakes. For example, minimize the number of keystrokes the user has to type. If you put in a list of selections, then the user is harder to make a mistake than if you put in a text box for the user to type in some text. Right? It's impossible to make a mistake when you provide a selection of courses for the user to select, rather than letting the user type in Comp211. It's easy to make mistakes if you type in many keystrokes. Reversibility. Actions should be reversible as much as possible. So you should try to gather all the user inputs and send them out to the database at the batch, so that during the data entry, the user can always click the back button and revise his entry without affecting anything. While if you collect every bit of a small piece of information, and as soon as the user enters it, you send it to the database, then the action is less reversible, right? So reversibility is good because the user reduces the user's anxiety. He knows that he can always do some undo action. Control, the user should feel in control, not the other way around. So the system should not take over control. To avoid surprising actions or tedious data entry, so without control, a user is likely to feel frustrated and anxious. So cognitive load. There's some study that says humans can keep roughly 7 ± 2 pieces of information in his head at any one time. Anything more than that would be difficult to keep track of. So to overcome cognitive load, you try to simplify your dialogue design. Don't design a super complex dialogue. Try to spread things up into several dialogues if one gets too complex. Reduce window motion. Don't let the user navigate too many steps to accomplish a task. Also, of course, provide online help, etc. And also, in the dialogue design we saw before, so this is a good design of a select courses to register because it has a lower cognitive load. You enter 6 courses, you click a button, you're done. Well, in the previous design, you have a higher cognitive load because you have to remember what you entered before. You have to click the button 6 times to register for 6 courses. So evaluation, we need to assess the usability of the UI and whether it meets user requirements. So it should be part of the testing process. Evaluation should be conducted against usability attributes. Part of design goals. So we learn about design goals very early in the course. You have many possible goals. Reliability, dependability, performance, throughput. So user interface usability has many attributes as part of the design goals, like learnability. How long does it take a new user to learn to become productive with the system? Of course, it depends on your user target. Speed of operation. How well does the system response match the user's work practice? Is the system so awkward to use that the speed is very slow, or does the system help the user? Robustness. Do you have many errors? Recoverability. So if user makes errors, can the system recover, or can the user kill the system by using the system? So systematic formal evaluation of UI can be expensive and time-consuming. So this is referring to hiring some perhaps cognitive scientists or psychologists who are studying human-computer interaction to do a formal evaluation. There's a whole research community of people who are studying HCI, human-computer interaction. But that is perhaps done for very high-volume products like Microsoft Office. For most products, you really can't afford to hire a specialist to do this formal evaluation. So most likely you do some informal evaluation techniques like questionnaires. You give the software to the user perhaps for beta testing, and after a month you send out a questionnaire to collect opinions. Observations, so you can watch the user at work either in person or on video, or you can have think aloud sessions. That is, people get together and discuss how they try to use the system to accomplish some tasks. So kind of a brainstorming sessions. Monitoring code to discover information. For example, you can insert logging code into your UI to record how many times the button is clicked, how many times the menu item is invoked. So if a menu item is invoked very often, then perhaps you should make a shortcut button for it. Bring it to a more prominent place on the UI. You shouldn't hide it behind many layers of menus. If something is used very rarely, perhaps you can highlight a few levels deep. So now we move on to validating requirements. So this is the acceptance testing phase. So requirements should be continuously validated with the client and the user. So they should be correct. That is representing the client's view of the system. Everything in the SRS system requirements document accurately represents an aspect of the system. Complete, that is all possible scenarios through the system are described, including exceptional behavior. So when you develop the SRS, initially you focus on the most important use cases, and gradually you add exceptional use cases to it. And eventually, at the end of the requirements stage, when you have the SRS document, you should the document should contain all possible scenarios. That is, if it's not contained in it, then you don't have to implement it. So consistent, there's no contradictions, unambiguous, so exactly one system is defined, not possible to interpret the SRS in two or more different ways. So because the SRS is really like a contract between the developers and your client, so it should be to avoid any disputes, it should be unambiguous. Realistic, that is, the system can be implemented within the given constraints. So oftentimes the client wants everything. And then as a software developer, you should tell them what is feasible, what is not, within the cost and time constraints. So correctness and completeness of their SRS are difficult to show. So therefore, we need acceptance tests. So tests must be specified to demonstrate to the client that all functions and constraints of the system are fully operational. So if you're just reading the document, it's hard to validate the system at the end of the delivery. So does the system satisfy the requirements or not? Right? You can get into disputes. But if you have acceptance tests, then if the test pass, by definition, the requirements are satisfied. So when at your Activity 1 demo, what you did is the acceptance testing. So first you test functional validity. Does the system provide the required functionality? So for example, for the use case of selecting a course offering to teach, you just try to log into the system, pull up the courses, select the course offering, and save it. And if it's successful, then this test passes. So that's the most fundamental test. Interface validity. So do interfaces, user interfaces, perform desired functions, accept desired input/output, and provide desired accept input and provide output, and follow any design standards. show that all the required data for course registration can be input. So if your dialog is missing some fields so that you cannot enter the semester, then it violates interface validity. Information content, are the stored data correct? So in the required format and obey the required constraints. So this show all the required information of a student's course schedule is correct by looking at the database after a student registers for a course. You can look at the raw database directly, look at the table directly, or you can do a later query to make sure that you pull up the correct information that you registered, that you entered before. So show that the student cannot register for more than 4 courses. So if your system is in operation, say for a month, and you find 20 students registered for 10 courses each, then obviously your system doesn't have the information content validity, doesn't pass this criteria. So performance, does the system meet specified performance criteria? So this is the non-functional requirement. Show the response time to register for a course is less than 1 second. This is easy to do for a single user system that you develop as part of your course project. But it's harder for real systems where it must handle thousands of users simultaneously. So that's when you use so-called stress testing to test the system under a very heavy load. Of course, gathering 1,000 users hitting the system at the testing stage is difficult. So what you can do is that you can write a script to generate many artificial workload to stress test the system. So how do you derive an acceptance test plan? So you take the requirements and specifically the flow of events of use cases and restate them in a concise, precise, and testable way. So because the flow of events is often ambiguous or very abstract, you need to fill in details and make it precise and testable. So you group related requirements perhaps into a single acceptance test and remove any requirements that cannot be tested. For example, something that's a mental process. A student thinks about course offerings to take. That is a non-testable requirement. Only the interactions with the system, with the computer system, is testable. Add any additional requirements gathered from the users by looking at use cases for functional and interface requirements. Domain model for information content requirements. The domain model describes the database, right? So a student cannot register for more than 4 courses. That is a domain model information content requirement. That's modeled as the multiplicity in the class diagram associations. Looking at non-functional requirements for performance requirements. So construct for each requirement an evaluation scenario that will demonstrate to the client that the requirement is met. So evaluation scenarios are based on user interface. So typically you do this after you design the UI. So they cannot be completed until the UI is designed. So here's the requirements. Essentially, flow of events for the student registers for courses use case. So first, you state it precisely. 1, 2, 3, 4, 5. First, request course catalogs. Second, decide courses to take. Third, you have some sub-steps. So you can possibly write this as a sub-flow, or you can pull it into the main flow. Both are okay. So this is the main flow style. And then you select up to 4 courses and select 2 alternative course offerings, and etc. And registration system sends information to the billing system, and then courses to teach. So here, this requirements actually groups the students register for courses and select courses to teach into the same flow. So because they're very related, and you want to design acceptance tests to test both functionalities with one test. So restate it in a testable way. So the first line says students can request course catalogs containing course offerings for the semester. In a testable way, you'll say the system must be able to produce a course catalog containing course offerings for a semester. So you turn it from a different perspective. The system must be able to produce. Then you can test it by actually letting the system produce a course catalog. Could be just a screen display, could be a PDF file, could be something else. So the second line says students decide which courses to take. This is a mental process of the student. Therefore, it is not testable. So we delete this line. And the next course registration has this 6 itemized requirements. So students, this is essentially a copy of the previous slide, because all of these are testable. So you can select up to 4 course offerings. Just select 4, and less than 10 students will be cancelled. You can try registering for less than 10 students, and when the time passes the add-drop period, it will be cancelled or not. So then the step 4, the registration system sends information to the billing system. So in a testable way, you say registration system sends the following information to the billing system for each student, including student's ID, surname, other names, etc., the code, title, and credits. Comp211 software engineering 4 credits for each course offering in which the student is enrolled. So in the previous version where you say send information, but what information? It's not testable. By stating it in a precise way, you can write a test case for it. And last, professor can choose courses to teach and request class lists for the courses they are teaching. So these are okay, they're copied from the previous requirement. So there will be other requirements that have been gathered from the user. So And then you can design test cases based on the testable requirements. So this is done at the inception phase. So for the first item, you demonstrate that the system can produce a course catalog containing course offerings for a semester. So that is a test case. And for course registration, the first one says students can select up to 4 course offerings. That's the requirement. And in the test case, you say, test plan, you say, demonstrate that course offerings can be selected up to a maximum of 4. Essentially, it's the same thing. It's just expressed in a way like an instruction. So this is what's given to you at the activity 1, perhaps a demo stage, when we give you specific instructions as to what to do and see if you can do it or not. And then demonstrate that alternative courses can be selected, a course can be created, and a course offering can be added to a existing schedule, drop, and no more than 40 students. So notice 2.5 in the previous testable requirements, we say a course offering cannot have more than 40 students enrolled. That is a requirement statement. But we need to write a test case for it. The test plan says enroll students in course offerings and show that no more than 40 students can be enrolled in any one course offering. So this is a more action-like statement, more executable statement, while the previous one is a more declarative, even though they describe pretty much the same thing. So this is saying, okay, enroll students in course offerings, try it for 41 students, and see what happens. So this is something that's very concrete, that it can be tested. So enroll less than 10 students and show that it is canceled at the end of the registration period. So this executable test plan actually validates the previous non-executable declarative requirement. So send information to the billing system. So demonstrate that the registration system can send the required information to the billing system. So actually send it in your system. And courses to teach. So demonstrate that professors can choose courses to teach, can display class lists. So for most of these items, you just add a demonstrate that in front of the requirement to make it more kind of executable. So the acceptance test plan is started in the inception phase and refined and completed during the elaboration phase. So the final acceptance test plan is closely related to the user interface design. So this is the what I described just now is the one you design initially in the inception phase. In the inception phase, and eventually you will refine it and complete it later in the next elaboration phase by adding more UI-specific elements to it. So actually, say, invoke this menu item and pop up that dialog box, and so on. So this one is still pretty abstract. So retrospective, we're done with the requirements chapter. So we discussed first, domain modeling captures the static requirements of an application. Essentially, you're designing the database. it is a class diagram that shows classes and relationships between among the classes. It has a direct translation into the database schema. So it acts as the vocabulary data dictionary for pretty much all the other models that you will develop later. So use case modeling captures the dynamic processing requirements of an application. So a domain model is a static thing. So use case model actually describes what the actions are happening in the system initiated by an actor. So a use case model shows the use cases that provide the system functionality and the actors that use the functionality. And flow of events describes the sequence of actions that comprise a use case's functionality. So that it describes what happens within each of the oval representing a use case. Essentially a step-by-step list of actions. So also we described subflows. You can write a whole long flow of events, or you can pull them out into subflows to make the main flow shorter and easier to understand, like procedure calls. We also described alternative flows where you can model exceptions. You specify the main flow, 30-day scenario, everything goes smoothly, nothing goes wrong, and then later you add on some exceptions. What if the semester is entered wrong? What if the deadline has passed, etc.? These are described in the alternative flow. So we also described include use cases, where a use case can be shared among multiple other use cases, like validate user login can be shared between the professor select courses to teach and students select courses to take use cases, because they both need to validate the user, like enter a password. This is essentially mainly to reduce redundancy in your use case specification. Otherwise, you have to duplicate some functionality in different use cases. Then we discuss user interface specification and prototyping. So demonstrates that the UI meets all the stated requirements, including data validity requirements, including functional requirements and non-functional performance requirements. Requirements validation demonstrates the user meets all the requirements. How do you do that? You do it by designing acceptance test plan. Details how the user verifies that the requirements have been met. So this is how we grade your activities. So requirements are captured over several iterations by specifying a domain model, database, use case model, describing functionalities of the system grouped into use cases, acceptance test plan to validate the requirements and user interfaces, plus some UI prototypes. So it is desirable, even at the requirement stage, to develop a prototype like what we're doing now, executable prototype to show the user as part of the requirements process. So they're all documented in the SRS. So in subsequent iterations and phases, we refine and or transform the requirements by specifying more details for each one of the above artifacts. So remember, this is unified process. It's not waterfall, which means that you always go back to requirements at every top to bottom iteration. Whereas if it's waterfall, then requirements are fixed and you never go back. So that's the difference. And matching use case realizations in the analysis model and design model. So a use case specification in the requirements document, you must design a realization for it. That is, design the actual software structure to implement the specification. That's called a realization. Realization has multiple levels, from analysis model to design model to implementation. You go from abstract to more and more concrete. And also a set of test cases in the test model. The use cases drive the subsequent iterations and phases. If you recall the 4+1 view of the unified process, you have use cases sitting in the middle. You have 4 corners with the design model, implementation model, deployment model, etc. So everything you do after the requirement stage is driven by use cases. That is, when you design the analysis model or design model, you must ask yourself, which use case is this for? You must be able to trace every single thing you do back into a use case. So it's called traceability. So that's the end of requirements. Any questions? So the test is next week. It is in class. The test essentially has multiple choice questions and a question on class diagram design and a problem on use case diagram design. So I can tell you right now, it's not a secret. So just don't tell the people who don't come to class. So next class we will have a review class. Essentially, we'll go through multiple choice questions, and you should bring your PRS for two-way interaction. So we move on to analysis. So learning objectives understand the role and importance of system analysis. So know the main activities during system analysis. Learn how to transform a use case model into a form that is maintainable. Learn how to represent interactions among the objects and describe the internal behavior of objects and flow of control among objects. So now we're going into a computer science domain, into a software domain where you actually are designing the internals of the system. So now, from now on, the document you design, the analysis model, design model, etc., you don't have to show the user anymore. The user only cares about the requirements model. This is for the internal use among the developers. So, importance of system analysis. So the goal is to structure the use case model into a form that is robust and maintainable during the system lifecycle. So at this stage, we assume ideal implementation environment. Do not consider hardware, database management system, programming languages, and they're likely to change over the system's life cycle. So the word robust means that as you are developing the system, you may have changes in all these hardware, languages, etc., but they should not affect your analysis model. So so at this stage, we don't want the system's architecture to be affected by the implementation environment, so that this is a platform-independent model. So by ignoring the implementation environment, we reduce the complexity and make the model robust. So we specify the logical classes, parenthesis dynamic. So this is a class design, but it's dynamic class design, which means that it is different from domain models. Domain models are static classes. These classes are not mapped into databases directly. Dynamic classes and how they are related and grouped into packages. So you may have 200 classes in the analysis model. If you spread them into a flat level, it's very hard to understand. But if you group them into packages, you can divide and conquer to understand the system. So this is the object model. So at this stage, we really focus less on inheritance, association, etc., more on the objects, that is class instances, how they communicate and interact with each other. We distribute the behavior of the use case model among the logical classes of the object model. So it's called a dynamic model. So the use case model has a behavior as specified in the flow of events. Now you need to design these classes that collaborate to carry out these flow of events. So distributed behavior among different classes. Each class plays a role and does part of the job. So we specify explicitly which class is responsible for which behavior in the use case model. So why do analysis? Why not go straight to design and implementation? So the benefits are that it yields a more precise and complete specification of the requirements, removes ambiguities and redundancies, because the requirements are specified mostly in natural language, which are inherently ambiguous. Even though you try to make it precise, still the analysis model is expressed in a more precise way with UML. It's described in the developer's language, more formal and precise, as we'll show later with these diagrams. It's really like programming language, where you can have for loops, if then else, break, exceptions, etc. So it can be very formal. Structured requirements for easier understanding and maintenance. So you can package them or place them into packages. It's a first cut at a design model. So a design model is actually is more refined. It actually involves the platform details. So the design model really cares about do you have a distributed system? How many CPUs do you have in the system? How many offices does the company have, and how to distribute the software, etc. Well, at the analysis stage, we don't care about all that. We only care about functionality. But the analysis model can be a first cut. That is, you can evolve the analysis model into a design model. So what do we do with the analysis model? So keep it and maintain it throughout the system lifecycle. This is highly recommended. Throw it away after requirements analysis. After analysis stage is complete. So it's a transient intermediate tool that is really used as a bridge to the design model. After you get to the design model, you'll throw the analysis model away. This is perhaps okay, but it's not really recommended because the analysis model is platform independent, right? So in case you move to a different platform in the future, if you don't have the analysis model, then you have to modify your design model to accommodate the new implementation environment. But if you have the analysis model, you can start from the analysis model and design it for a new implementation environment. So it's more stable than the design model. Don't build it. This is not recommended. So if you don't build it, perhaps you should build more formalism into a use case model. That is, in your flow of events, perhaps you need to be very precise if you want to avoid the analysis model and go directly from use case model to a design model or to implementation. But natural language has its limitations. No matter how precise you are, it's not as good as what you described next, sequence diagrams. They are really more like programming languages. So this reminds you of prototyping, right? So for prototyping, we have opposite recommendation. Prototyping, you should throw it away and start from scratch and build a clean architecture. And keeping it is not recommended. But for the analysis model, you should keep it and try not to throw it away. So analysis is performed in the initial iterations of the elaboration phase. So this is early elaboration phase is its highest point in the diagram, which means that that's the focus. So here are the workers and their artifacts. Now you have architect. This is the new guy, right? Software architect. So he's the guy who's going to take the requirements document and develop the analysis model and architecture description. And you have a use case engineer who's responsible for use case realization dash analysis. So use case is found in the requirements document. Use case realization is the analysis model, the class design that realizes the use case. And dash analysis means that this is the analysis stage. And later in the design stage, you have another realization dash design. And component engineer is responsible for designing the analysis classes and grouping them into packages. So we won't do the architectural analysis in this course because our systems are too small. So we're just gonna do analyze use cases, analyze classes, and identify and analyze packages. So analyze use cases. So you should derive the analysis classes from use case. It's an abstraction of one or more classes in the final implementation. So in the implementation, if you're using Java or C++, you have many classes. So, but here we're talking about analysis classes. They're not implementation classes. One analysis class can turn into many design classes up to 5 times and eventually to many more implementation classes. So, for example, we may say professor interface as an analysis class to represent the boundary between the professor and the system. It may turn into maybe 20 dialog boxes eventually with hundreds of classes implementing these dialog boxes in the final code. So we focus on handling functional requirements only. That is, we ignore any non-functional requirements. They are specified as special requirements as annotations and handled at design and implementation. So we don't care about performance, throughput at this stage. So analysis class descriptions are conceptual, that is, not implementation oriented. They may have attributes. If you recall, classes have these 3 compartments, right? You have a name, you have attributes, you have operations. So of course they have an analysis class as a name. Attributes, they may have attributes there, but they're conceptual. That is, you can say anything you want. Salary could be money. So you don't have to say floating point or double or integer, etc. Behavior is defined by textual descriptions of responsibilities. So this is referring to the operations, referring to the operation part of the class. Usually it's specified as kind of function calls, right? Get salary, deposit money. But at this stage, we don't do that yet. We just use textual description in natural language to describe the responsibility of the class, not in the method call syntax. Relationships are conceptual, not implementation oriented. That is, you don't care about pointers, references. You only care about conceptual relationships. So as far as this class can talk to that class, that's all you care about. You don't care about how it's implemented. So one of the 3 following stereotypes: boundary, entity, and control. So stereotypes, if you recall, this is the additional annotation on your class to specify that it is a special class. So boundary class models the interaction between the system and its actors. So it looks like a circle with a little handle on the left side. So this is kind of like a boundary. On this side, these are actors, the outside environment. On the right side is the internal of the system. So this is the icon form, and then this is the class diagram form, where you have a box with a name with no attributes and no operations, only one compartment with a stereotype boundary. So these two are completely equivalent, except the one on the left is more intuitive. Just like the actor, the stick figure is really a class. You can draw it with a box with a stereotype parentheses actor inside of it. It's completely equivalent. We designed these icons for easy reading of the class diagram. Interacts with actors outside the system as well as objects within the system. Represents abstraction of UI elements, including windows, forms, pens, or devices like printers, sensors, terminals. So these are abstraction. That is, you don't care how it's implemented yet. So the output could be printed on a terminal, could be sent to a printer, could be sent to anything. So you only care about the conceptual thing of a boundary. The description should be kept at a high conceptual level. Describe what, not how. Do not describe every button, menu item, etc. of a UI. So describe what this class is intended to do, not how it's done. So the purpose is to isolate, encapsulate changes in the system's interface. So including user interface if the actor is a user, or communication interface if the actor is an external system. So so the reason you can do that is because the description describes what, not how. That is, you only care about that it is an interface between professor and the system. Later, when you change the UI design to have a different input interface, perhaps by using a pen-based interface versus keyboard or different output interface, these do not affect this boundary class. It's very abstract. So how do you identify boundary classes? So you start from actors in the use case descriptions. Identify forms and windows needed to enter data that is input into the system, and notices and messages the system uses to respond that is output from the system. Do not model the visual aspects of the interface. That is the actual dialogue. Keep it abstract. Always to use the user's terms for describing interfaces. So because it is it is interacting with the user. So the specification strategy is to initially identify one boundary class instance that is an object. So class instance is equal to an object, just two different ways of saying the same thing. For each actor use case pair, so for human actors, it represents the primary UI with which the user interacts with the system. So for external system, it represents the communication interface to the external system. So initial boundary objects can be later aggregated or become aggregations of other boundary objects. So initially, because you are putting in one boundary object for every user use case pair, but many times when a user can perform multiple use cases, perhaps you want to merge these objects into one. Notice here we're saying really identifying boundary classes, but we're really talking about class instances, that is objects. We don't make a huge distinction here because really we care about the instance level at this stage. We draw the class diagram, but what we care about is actually the objects that are instantiated at runtime, because you are designing the runtime stuff. What happens when you actually click a button, the object gets invoked, etc. So you're not designing a conceptual database where the classes are the key concepts, not objects. Here we have objects at the center. So here's the use case, Professor Actor, which has he takes part in two use cases: select courses to teach and request enrollment list. So the rule is for each actor use case pair, you instantiate one boundary class. So you just attach the word UI at the end. Select courses to teach UI is the name of the boundary class representing the interface to the select courses to teach use case. Possibly later, you can merge them into a single analysis class with composition or aggregation relationships. So it turns out both of these boundary classes are used by the Professor Actor. So then perhaps you can merge them, and perhaps you can refine them later. So select courses to teach can be refined into create schedule, review schedule, and modify schedule. So, and then perhaps each one is a different dialog box. Perhaps from this dialog box, then you click a button, make a selection, and pop up one of these three, depending on the action selected by the user. So that's for later refinement. Right now, we're just doing conceptual design. So entity classes models information that's long-lived and often persistent. This is really database stuff. So this looks like a ball sitting on the ground. It means that it is something concrete. It actually sits there, right? So, or you can have an entity stereotype. Represents objects, concepts like individual real-life object or real-life event. So we'll likely get its data from a database, but it represents a dynamic object in the analysis model. So notice the distinction here. So in the database, you have student table, right? And it is designed with the class diagram in the domain model. And then you map it into database schema, and you fill in the database with perhaps 200 students. So that's a table sitting on the disk. Now, when you invoke your system, run it, and a student logs in, say a student named Jim, he logs in and pulls up his record. Now what happens is that the system issues a SQL query to the database and gets the data, student information named for this particular student. And in your code, you say new student, parentheses, student name, age, and all the other attributes in the constructor based on the information in the database. And then you can, that is the entity class instance, the dynamic object. And then when you are done with the with your work, you can say save information to the database and then delete the object. And then the information is updated in the database table, and your dynamic object student is deleted, right? So the entity object is this runtime thing that is created and deleted at runtime with a correspondence with this database table, but it is transient. That is, it gets this data from the database, and when you are done, when you log out, it is destroyed. So it encapsulates and isolates changes to the information it represents. That is, the keyword here is information. That is, encapsulates the student information. Say, for example, if you later modify your domain model and modify your database schema to add a new attribute to the student, and then you just modify your entity class design to reflect that change. As a result, all your other classes in the system does not have to worry about this change. So compare this to the previous slide where we had encapsulate and isolate changes to a boundary class encapsulates changes to the UI. I think it's somewhere. No, we didn't say it. So the boundary class encapsulates UI, while the entity class encapsulates the data. So the specification strategy, again, is going from the domain use case model to determine what domain model classes are accessed to carry out the use case. So for this example, professor select courses to teach. You examine the scenarios of a use case to determine what domain model classes are needed. Remember, scenarios are concrete instances of use cases. So you have this boundary class we identified before. Now you look at the scenarios. Select courses to teach. What do you need? Of course, you need the core. You need the course, domain model class, and course offering, and professor. So these are the entity classes you design for this particular create schedule select courses to teach scenario, use case. So these are, again, I emphasize, these are entity classes. These correspond to the classes in the domain model, but they are different. They are dynamic. They are created and destroyed at runtime. So control class looks like this. Is kind of like a cycle with an arrow, right? It means that it's going round and round. It's something that models the coordination sequencing and transactions and control behavior. That is, it really acts like a conductor in an orchestra to coordinate everything. A control class instance, that is the control class object, usually does not have a correspondence in the application domain. They are purely a software construct to help you implement your stuff later. Provides the glue that ties together other classes together into one use case realization. So a use case realization is a collection of analysis classes, mainly glued together by the control objects to carry out a particular use case. A use case, a control class object instance is used to represent control related to a specific use case. That is the what is control? We're talking about control flow. In the C program, the control flow is done with if then else while for go to etc. So we're talking about where the control goes. And business logic, like complex derivations and calculations that cannot be related to a long-lived class. So in this course, we're mainly focusing on this one, not the business logic role of the control class. So encapsulates and isolates changes. You saw these words 3 times now. So this one encapsulates control and business logic. So here's the strategy. Initially assign one control object for each actor use case pair, and for each include extend use cases, if you recall, that is responsible for the flow of events in the use case. So complicated behavior may need several control objects, can combine, eliminate some control objects. So we handle these later. So we add these first. Control object should only be tied to at most one actor, because changes in system requirements are often initiated from actors. So by associating a control object to at most one actor, we isolate the changes required to only the functionality needed by that actor. So remember, the control objects are intended to encapsulate the control logic. Therefore, if you have multiple actors sharing a control object, what happens? Then you don't have good encapsulation, right? So one actor's change can affect the others. But by associating one control object to at most one actor, of course, one actor can be tied to many control objects. Then you can isolate changes when some actor changes its requirements. So sometimes it's better to encapsulate the control in the boundary object, especially if the actor handles large parts of the control. So this is a so-called fat client versus thin client, right? If the client, if the UI is very complex, then perhaps you can reduce the complexity in the internal system. So this is only applicable if you have a relatively simple systems. For most reasonably complex systems, you should design control objects, dedicated control objects. So here's the example where we have designed the boundary class and 3 entity classes. Now we add 1 control class for each actor use case pair. So actor, professor, use case, select courses to teach UI. Then we add 1 select courses to teach manager. We say manager because it manages the interactions among the UI and entity classes. So how do you connect the boundary control and entity classes? So essentially the idea is that the boundary classes should talk to the control classes or objects, and control objects talk to the entity objects. And control objects should not talk to control objects themselves. So you kind of have a 3-tier architecture: UI, control, entity. And user only interacts with the UI objects. So it's a very clean tiered system. So we'll discuss more details after the midterm. So next class we'll have a review class.